concepts video on the section on power and polynomial functions. Okay, so the first thing we're going to go over is a power function. Okay, so power function. So what is a power function? It has the following form of f of x, or g of x, or whatever function name it is equal to x to the p, okay, where we have that x is our variable, x is a variable, so you could just as well have like t to the p or something like that, okay, and p is a constant. Okay, and its specific name, because it's up there as an exponent, its specific name is called your power, okay, hence the name power function. Alrighty, so some examples, we've seen plenty of these. We've seen like f of x is equal to x to the third, that's our cubed graph, right, something like that. We've seen x squared, that's of course our quadratic function. Alright, so this one is our like parabola, right. We've also seen a linear function, that's just a line. Right? That's x to the 1 power. We've also seen, believe it or not, x to the 0 power, and this is just equal to 1. So that would be like a constant function at the height y equals 1. Okay? We've also seen when we have the negative powers as well. So x to the negative 1, that one's a little bit different, right? We have something like, looks like this a little bit. And then we've also seen are the reciprocal, too, of the x squared. So that one kind of looks the same, but it's a little bit steeper. Okay? So anyways, so we've seen lots of these throughout our time so far. Okay, so now let's break down the power functions into two separate groups. So we have, first of all, we have even numbered powers. Okay? So what does that mean? That just means your power is an even number, right? So for example, let's say we have our x squared. We have like x to the 4th, x to the 6th, and like x to the 8th, and so on. Okay, so x to some even power. So the thing is, when we graph these, let me show you the graphs of these just so we can get an idea. So x squared looks something like this. It's a u that crosses the origin, then it comes back up. Okay, so this is our x squared one. X to the 4th looks similar. It's kind of like this, and it does something a little bit funny in the middle, and then it goes back up. Okay, so this is x to the 4th. X to the 6th does the same thing, like this, does something in the middle, and then it goes up like that. Okay, that's x to the 6th. And then x to the 8th, it just keeps going on and on and on, and gets a little bit more narrow and narrow. That one looks a little weird, so I'm just going to redraw that. So, something like that. Okay, so this is our x to the 8th. So, kind of ignoring like what's going on in the middle, like by the origin. But in the long run, what we have is we see, well, as x goes to positive infinity, which means like that way, then our function is going up to infinity, right? So we're just looking at the right-hand side at this point. Okay, so as x goes to positive infinity, our function is going to positive infinity as well. Okay, now as x goes to negative infinity, or we also denote this as x goes to negative infinity, right? Then we see that our function value is also going all the way up to positive infinity. So we see f of x goes to positive infinity. Okay, so let me just write both of those classifications here. So f of x goes to positive infinity. Another way we could kind of just consolidate these notations into one simple one is we could say, well, as x goes to positive and negative infinity, then we have our f of x, our function values, going to positive infinity as well. Okay? So we could also see that, I'll show you on the next slide. Let's say we have negative x squared for some reason, negative x to the 4th, negative x to the 6th, negative x to the 8th, etc., etc. So now we would have something that looks different, right? So here's our x and here's our y. So now our parabola would be flipped upside down. Okay, so this is our x squared, so negative x squared in this case. And then we have negative x to the 4th, which looks something like this. And that was pretty bad, but we're getting the general idea at this point. Right, so then something like that. So everything just flips, right? This is a vertical reflection. So negative x to the 6th and negative x to the 8th, something like that. Okay, so they're all just pointing downward instead. Okay, so now we see, well, as x goes to positive and negative infinity, then our f of x, the function values, are going to negative infinity, right? Because they're all going down on both sides, right? As x goes this way and as x goes that way, then our function is going down, down, down. Okay, so let's look at the characterization then of even numbered powers, okay? So we can say from these examples here that we've studied, even numbered powers, or even powers we could say, even powers have the same what's called long run behavior, okay? And that term is pretty self-explanatory. I mean, it just means, well, how is your function behaving, or what is it doing in the long run? Long run meaning as x goes to, i.e., x goes to plus and minus infinity, okay? Plus or minus infinity, okay? So now let's look at odd-powered functions, the other categorization. So odd-numbered powers, okay? So in this, normally we kind of just exclude x to the 1, but we can look at it as well. So x to the 1, x to the 3rd, x to the 5th, x to the 7th, and so on, right? So let's look at the graphs of these. So we have x and y. So our x graph just looks like this. Okay, so that's pretty constant and boring. Linear functions are fun. But and then we have our x to the 3rd, which looks something like that. It's a little more exciting there, right? And then we have x to the 5th, which looks a little bit steeper of a slope, okay? Then we have x to the 7th, so it kind of keeps getting more narrow and more narrow. So the thing here to note is that, well, as x goes to positive infinity, so as x goes to positive infinity, which means goes to the right, our function values are going up, right? So f of x is going to positive infinity as well. But on the left-hand side, what we see is when x goes to negative infinity, so when x is going all the way to the left, like this way, our function values are going down. They're dropping, right? So f of x goes to negative infinity. Alrighty? So this one's different because we have that unlike, or like non-similar, right? So unlike long run behavior on either side. Behavior. Unlike, or you could also say opposite. On either side, right? It's not the same as x is going to positive versus negative infinity, okay? And also, just another little note, I'll touch upon this really quickly. If we have the negative of each of these, they're just going to flip, and so the left side's going to go like this instead. Left side's going to go up, and I did not go through the origin there. Okay, let me try to draw a line first. We're just going to pretend that's a line. Okay, with a slope of -1. So then we also have our x to the 3rd. This is negative x cubed, and this is like negative x to the 5th, so they just flip, right? There's going to be a horizontal flipping here, okay? Well, a vertical flipping, actually. So anyways, so this is what that's going to do, all right? And again, on the left side, we have x going to negative infinity, then our function value goes to positive infinity, okay? So as x goes to positive infinity, then our f of x is dropping down to negative infinity, right? So as we go this way, our function values are going like that. As x goes this way, function values are going up, okay? So the thing to note with odd is that the long run behaviors on both sides of the graph, they are unlike each other, okay? Alright, so now that we've covered power functions, we'll go over some things about polynomials. Polynomials. So the first thing that we should go over is, what is a polynomial? That sounds fancy, right? So basically what a polynomial is a sum of terms consisting of power functions. Consisting of a transformed, well, the technical definition is a transformed, and I'll just show you why. So transformed power function. So the things that we just saw, right? Any variable being raised to a constant power, right? With a positive whole number power. Okay? So, what do I mean by this? That means that x to the -1, those guys aren't allowed. X to the -2, those are not allowed. Let's see, what else do we have? X to 0, that's allowed. That's fine. Because we do have a term like that. Okay, so the general form for a polynomial is the following. F of x is equal to a0, or a0, plus a sub 1, x to the 1, plus a sub 2, x to the 2. And then you just keep going along, where this little subscript matches the power, right? And then you get to a sub n, x to the n, all right? So this is admittedly super confusing, because it's like, what are a's and what are the 2's down here? I don't know what's going on. So basically, the a sub i's, where that just means a notation where these guys are all different. They're all distinct, right? That's why we're numbering them. Anyway, so each of these are called coefficients. Coefficients. And they're just constants, okay? Like numbers like 2, 3, 4, whatever. They're coefficients that can be, they can be positive, they can be negative, or they can even equal 0, okay? And they can be whole numbers, they could be decimals, or they could be fractions, okay? There's no restriction on what our coefficients can be for each of our terms, okay? And now let me go over an actual example, like a concrete one.